Hello, students. Today we are going to talk about electromagnetic field theory. Fine. So let us see what will be the outline. So the outline of electromagnetic field theory will be the introduction, Maxwell's equation in differential form, and Maxwell's equations in integral form. Okay. Now let us see what are the prerequisites required. See, we need to revise few of the basic laws that you have also gone through in your class 12 standard. The laws are like Gauss's law of electrostatic, Gauss's law of magnetostatics, Faraday's law, Ampere's circuital law, Gauss divergence theorem, and Stokes theorem. So before going to the electromagnetic field theory, the concept and the introduction, all the Maxwell's equations, what we will do, we will just have a quick revision on these basic laws. So first and foremost, we start with Gauss's law of electrostatics. What is the Gauss's law of electrostatics? Yes, I think all are remembering. Very nice. Gauss's law of electrostatics states that the total electric flux, phi E, enclosed by a closed surface is 1 by epsilon naught times the total charge Q enclosed by that surface. So what is phi equal to? Q by epsilon naught. Okay. So it is stating that the total electric flux phi E enclosed by a surface is 1 by epsilon naught times the total charge Q enclosed by the surface. So Q by epsilon naught. What is epsilon naught over here? Epsilon naught is the permittivity of free space. Now let us go to the next law. Gauss's law of magnetostatics. What does that states? It states that the magnetic flux entering a closed surface is always equal to the magnetic flux leaving the same volume. Okay? The magnetic flux entering a closed surface is always equal to the magnetic flux leaving the surface of the same volume. What is phi b equal to? When the magnetic flux entering and the leaving is same, but of course the phi b will be is equal to 0. Now let us see what is Faraday's law of electromagnetic induction. Whenever the magnetic flux linked with a circuit is changed, an EMF is induced in the circuit. Okay. We all know that whenever the magnetic flux linked with the circuit is changed, an EMF is induced in the circuit. What is the magnitude of that induced EMF? The magnitude of induced EMF is directly proportional to the negative rate of variation of magnetic flux linked with the circuit. Okay. So what is it? Then E is equal to minus d phi b dt. Okay. So what is E? E is over here the induced EMF, and phi b is again we all know that it is the magnetic flux. Okay. Now let us talk about what is Ampere's circuital law. According to the Ampere's law, the line of integral magnetic field B along a closed curve is equal to mu naught times the net current through the area bounded by the curve. Okay, so what is Ampere's circuital law? According to that law, the line integral of magnetic field B along a closed curve is equal to mu naught times the net current through the area bounded by the curve. That is, line integral B dot dl is equal to mu naught I. Okay, so when we will be talking about Maxwell's equation, we will be seeing further use of Ampere's circuital law or the modification of Ampere's circuital law. So when we will be talking about that, I'll let you all know. Now next see Gauss divergence theorem. This theorem is used to transform a volume integral into surface integral. The volume integral of the divergence of vector A, suppose, over any volume V is equal to the surface integral of A taken over the surface S. So how we can write this? We can write that volume integral divergence A dV is equal to surface integral A dot ds. Then let us see Stokes' theorem. It relates the line integral to a surface integral over any surface of which the line integral path is a boundary. So what does this theorem states? The surface integral of the curl of a vector A taken over any surface S is equal to the line integral A around the closed surface, forming the periphery of the surface. Okay, so how we can write this theorem? We can write that surface integral curl A dot ds is equal to line integral A dot ds. Now you might be thinking that why we are talking about these, basic laws over here. When we will be, talking about Maxwell's equations, or we will be deriving Maxwell's equations in integral form or in differential form, there you will come to know the use of Gauss divergence theorem also and Stokes theorem also. And we will also see that these Maxwell's equations are related with these basic laws, of Gauss laws of electrostatics, Gauss law of magnetostatics, Faraday's law, Ampere's circular law. These four basic laws are the pillars of Maxwell's equations in integral form and in differential form. So it is very necessary to revise these laws. If we'll not be clear with these laws revision, then you will be having a bit of difficulty in deriving these derivations of Maxwell's equation, or you will not be able to then connect with these Maxwell's equation. Okay, so the revision is very necessary of these laws. Now, when we are talking about electromagnetic field theory, so what is the word? The first word that is coming to us is electromagnetic. If I say that let us talk about electromagnetic, let us have a abbreviation of electromagnetic as EM. So over here, electromagnetic field theory says we are something talking about EM field theory, electromagnetic. EM is electromagnetic. And if it is a field theory, it means we are talking about EM waves, electromagnetic waves. The importance of electromagnetic waves. Before any before any chapter we begin or before any unit we begin, you should always know why are we talking about that unit. Why that is there, we are going in the syllabus, or why we need to talk about that unit. So over here, first and foremost, you should know the applications of electromagnetic waves. Then only you can connect that we are talking that electromagnetic waves in the field theory. See, now we all know how the spectrum of electromagnetic waves. You can see the where the spectrum of electromagnetic waves is, we have taken a diagram. So over here, that these are from radio waves to the gamma ray waves. Okay. Now, if you see the applications, gamma ray waves are also very necessary in all these terrestrial gamma ray flashes. It also helps in PET scan. X-rays, everybody is knowing that what are the uses of X-rays. The X-rays are also EM waves. What are the use of X-rays? We are well known, all the scannings are also done through the X-rays, whether it is in medical or anywhere else. Then we all also know the importance of ultraviolet rays that we are getting from the sun. Fine. We know the visible region. Okay, it is from 400 nanometer to 800 nanometer. We know the visible region and the use of electromagnetic waves over here also. Then we all also know the infrared electromagnetic waves, the applications of infrared electromagnetic waves. We know the TV remote control or the night vision goggles all are, there in the applications of infrared electromagnetic waves. We know the importance of microwave electromagnetic waves. They are used in aircraft communication plus microwave oven. We are and very well known about the radio waves. Okay, we know what are the applications of radio waves. So many, if we see the spectrum of electromagnetic waves, we are clearly able to see the applications also of that electromagnetic waves. So when so much of the application is going on, then why not to study about that electromagnetic field theory? It means that EM waves that we are talking about, they can travel. So let us, we'll be having nice if we talk about the traveling of those electromagnetic field, electromagnetic waves in the field in terms of equations. Fine. So in the further slides or in the further communication, I'll be talking about the electromagnetic waves, the use of those electromagnetic waves in terms of equations, how the Maxwell's gives those equations, and today see so many of the applications are there of EM waves. Even currently, students, wherever you all are sitting, there are also electromagnetic waves that are surrounding you. Fine, I'm also sitting. I know I'm surrounded by the radiations that are coming out of the laptop. I'm able to communicate because of those electromagnetic waves only. So wherever we are sitting, all we are connected with the electromagnetic waves. If you're even sitting at home, you know that the radiation is coming out of the TV, the radiation is coming out of, if you're listening any FM or something like. So every way, the EM waves are there. So we will be talking about those EM waves in electromagnetic field theory. So over here are the references. This diagram has been taken by this blogspot.com. And for any references, you can see these books.